Hello everybody, my name's eMoney. Welcome back to my YouTube channel. Today we're going to cover chapter 13, which is the last chapter for Organic Chemistry 1. Yay! And I'm also recording this as the last video to complete both my OChem 1 and OChem 2 series, so I'm super thrilled. But anyways, let's just hop right into it. Chapter 13 is going to be all about the structure, properties, reactions, and preparation methods of both ethers and epoxides. And we're going to just go ahead and start first and foremost with ethers. Ethers are compounds that exhibit an oxygen atom bonded to two R groups, where these R groups can be alkyl, aryl, or vinyl groups. The geometry of an oxygen atom in an ether is very similar for water, alcohols, as well as ethers. And the exact bond angle kind of depends on the groups attached to the oxygen atom, with ethers having the largest bond angle. An ether can also act as a hydrogen bond acceptor by interacting with the proton of an alcohol. So just some quick basics about ethers. Most importantly, the definition of an ether. Now, ethers, something really cool about ethers, and I like this, they can interact with metals that have either a full positive charge or a partial positive charge. For example, Grignard reagents, which we covered last chapter, they're formed in the presence of ethers, such as diethyl ether. And the lone pairs on the oxygen atom serve to stabilize the charge on the magnesium atom. The interaction is weak, but it is necessary in order to form a Grignard reagent. Now, scientists discovered that the interactions between ethers and metal ions is significantly stronger for compounds with multiple ether groups. Such compounds that have multiple ether groups, are called polyethers, many ethers. All right. Now, through the investigation of the properties of many cyclic polyethers, such as crown ethers, which are shown right here, their molecular models resemble kind of like crowns, and metal ions can actually be solvated by these crown ethers, which is really cool. So you can kind of like put in a little metal in there and have these crown ethers solvate the metal ions, like lithium or something like that. So I thought that was a really fun fact about crown ethers, and I wanted that to be part of our introduction into ethers. But with that, that's pretty much our basics for ethers. What we're going to get into now is discussing preparation methods for ethers. Now, industrially, the industrial preparation of ethers follows a acid-catalyzed dehydration, and specific acid-catalyzed dehydration of ethanol. The mechanism of this process is believed to involve an SN2 reaction. A molecule of ethanol is protonated and then attacked by another molecule of ethanol in an SN2 process. As the final step, deprotonation generates the final product. Notice that the proton used in the first step, all right, and then and the proton that is liberated in the last step is conserved. The acid is therefore a catalyst, not consumed by the reaction, and it enables this SN2 process to proceed. So this is kind of how ethers are prepared industrially. Now, another way to prepare ethers, they can be readily prepared through this two-step process that has a name, and it's Williamson ether synthesis. In the first step of this mechanism, what you will see is that the alcohol is deprotonated to form an alkoxide ion right here. And in the second step, this alkoxide ion functions as a nucleophile and then attacks an alkyl halide in an SN2 process. So the alcohol essentially loses the hydrogen to gain whatever R group is part of the alkyl halide in solution. All right. And another way and final way of that we're going to talk about for preparing ethers is through this process called alkoxymercuration demercuration. All right, very similar to something we've covered in chapter 8, where we talked about alcohols can be prepared from alkenes through a process called oxymercuration, demercuration, where you have a marked addition of water, hydrogen and alcohol across the double bond. Here, if we replace the alcohol is used in place of the water, then the result is going to be the marked addition of an alcohol across the alkene, where you add an OR group to one side of the double bond and a hydrogen to the other. So in oxymercuration, demercuration, to the double bond, we added OH and H. We essentially added water to the double bond, right? Now, we can have this variation of it where we actually add a alcohol group, where the OR part of the alcohol, the oxygen and whatever R group is attached to it, gets attached to one side of the double bond and the hydrogen on the other side. As a consequence, you form an ether. All right, so this is the derivative of oxymercuration, demercuration, alkoxymercuration, demercuration. Fantastic. So with that being said, let's actually do a few practice problems with some of these concepts we just talked about. Show the reagents you would use to prepare each of the following ethers via Williamson ether synthesis. Let's go back here for a second. All right, you want to form a specific product, which is going to be an ether. It's going to have an oxygen with two R groups attached. In order to form this ether, what you want to start off with is this R group to the oxygen. All right, but now the oxygen has a hydrogen instead. Then you treat it with sodium hydride. All right, fantastic. And then an alkyl halide, where the R group in that alkyl halide is the group you want to replace the hydrogen of the alcohol with. Okay, so keep that in mind. We're going to look at this. We're going to look at A. This is the end product. This is the end ether we want. Okay, so we need to use this William ether synthesis to do that. What we can do is, taking at the oxygen, kind of cut this, and we could take either half of this. It will work. I'm just going to take the left half. All right, here's the left half with the oxygen. I'm going to add a hydrogen. Okay, this is the alcohol we want to start off with for this Williamson ether synthesis. Then, of course, I'm going to treat it with sodium hydride. All right, but then what is the alkyl halide I want to treat it with? It's just going to be the other half of what was on the oxygen. So we see this group on the other half of the oxygen, and I'm going to be attaching that to some halogen, say iodide. All right, fantastic. This is what I need in order to prepare the final product that they asked me for. And ta-da, we did it. That's it. All right, pretty simple. I'll let you do B since it's a derivative of A, and then we're going to do C together. Okay, so let's see what we have for C. Fantastic. All right, what we can do is, again, at the oxygen, cut in half. All right, easy peasy. So that means what we want to start off with as our alcohol is something that's going to look like this. Okay, what we're going to treat it with always sodium hydride. And then for the second part, what's our alkyl halide? Well, what's attached over here? Just the methyl. All right, so just the methyl, and I'm going to attach that methyl to, say, iodide again. And then when we react this all together, we're going to get that end product we want. Fantastic. So that is how you solve these types of questions. Let's do some more. Identify the reagents that you could use to prepare this ether through alkoxymercuration, demercuration. All right, so they're telling us what kind of reaction they want us to do. So let's figure out what the reagents that we're going to need for this are. All right, here is our double bond, and we're going to be adding an OET to this and a hydrogen to the other side. Okay, that pretty much gives us our answer. So now the reagents that we would need are very similar to oxymercuration, demercuration, in the sense that we preserve some of the same stuff, this mercury, OAC2. But now instead of H2O, which is what we did before when we were trying to hydrate a double bond, instead of that, we're not hydrating, we're trying to form an ether. So we're going to take the OET group that we want to add the ethoxide group and the hydrogen, and we're going to treat this with ethanol now so that the ethoxide group gets added to one side of the double bond, the hydrogen on the other, and then we're going to use sodium borohydride, of course. Fantastic. So this is the set of reagents you would need to conduct this reaction. All right, so now we've talked about preparation methods of ethers. Let's talk about reactions of ethers. There's going to be two we're going to talk about and focus on. First, acidic cleavage. All right, whenever you have an ether and you heat it up with a concentrated solution of strong acid, so heat and strong acid, treating your ether with it, what will happen to your ether? It's going to undergo acidic cleavage, in which the ether is now going to be converted into two alkyl halides. So what that means is every R group that was once attached to your oxygen to form your ether, each one will go out in its own to form an alkyl halide of some sort. All right. So when you treat an ether with a strong acid and heat, you're going to form two alkyl halides. All right, this involves two substitution reactions. The mechanism involves two big steps. All right, the first one is formation of your first alkyl halide, which proceeds through proton transfer and then an SN2 reaction. The ether is protonated. It generates this oxonium ion, which your halide comes in and functions as a nucleophile to attack it and eject the alcohol as a leaving group. And it forms your first alkyl halide, and then it happens again to form your second alkyl halide. Same thing, proton transfer, then SN2 reaction. All right, so that is the first reaction we're going to talk about, acidic cleavage. Once again, you treat your ether with concentrated, strong acid and heat. It will go through acidic cleavage, where you form two alkyl halides out of your ether. All right, and this involves two substitution reactions. Now, if either R group is tertiary, then the substitution is more likely to proceed through SN1 process than SN2. Just keep that in mind. All right, next we're going to talk about autooxidation. Okay, ethers can undergo autooxidation in the presence of atmospheric oxygen, all right, to form hydroperoxides. All right, this proceeds through a radical reaction. We're not going to focus too much on the radical reaction here, but we talked about radical reactions: initiation, propagation, termination. Your initiation forms a radical. Okay, then your propagation step occurs through here coupling and hydrogen abstraction, where your net reaction is the sum of your propagation steps. So in this first coupling step, you form a carbon radical couples with molecular oxygen to form this. All right, you start off with this in the second step, where a hydrogen abstraction occurs. Notice how this molecule appears as a product in one step and as a starting material at the end step, so they cancel out. All right, and this radical that you formed in initiation appears as a starting material in one reaction and end product in the other. All right, and ultimately, your net reaction boils down to these two things as your starting materials and this as your end product. All right, and then your termination, where you now couple two of the radicals you formed to end the process. All right, so let's take what we just learned about the two main reactions that we learned about ethers: acidic cleavage and autooxidation, and let's do some practice problems that relate to those two reactions. All right, so this first one says predict the products for the following reactions. Fantastic. So we're starting off with this ether. We're treating it with excess strong acid, HBr, and heat. So what's going to happen here is, well, this is symmetric, so both of the R groups are exactly the same. What's going to happen is we're going to take an R group, all right, and it's going to attach to the bromine now. All right, so that's what this side forms. This other side, again, it's symmetric, so you're going to have the same product twice. Again, you take the same side, it's going to attach to bromine. You form the same thing twice, all right? Because remember, when you treat with strong acid and heat, what happens to your ether? Well, whatever two groups are attached to your ethers, they're going to form alkyl halides, all right? So you take the R group and you attach the halide in the acid that's used, all right? So we're treating with hydrogen bromide. All right, bromic acid, we're going to take the R groups and we're going to attach bromine to them. These are the two alkyl halides, which are exactly the same, by the way, because we have asymmetrical ether. These are our products. All right, let's do B. Same concept. All right, that means our oxygen gets cut in half. Well, it's a ring, okay? So now it has these two open ends, both of which are going to be attached to the halogen. All right, so we still form alkyl halides from both groups, right? Because when we cut our oxygen, it looks something like this. All right, if we cut it in half minus the oxygen, both sides are going to be treated with, here it's HI, so the iodine is going to be added here. All right, so that's our product for B. Fantastic. Let's do C. All right, here's C. All right, again, we're treating it with strong acid and heat, so we know this is going to be our acidic cleavage reaction. Our oxygen, we cut it in half. Whatever R groups are on each side, we attach to bromine because that's what's present in solution, and we get those two alkyl halides. So one will be like this. That's from this side. All right, fantastic. And then from the other side, what we get is an alkyl halide that looks like this. Fantastic. Alrighty. Awesome. So now that we've talked about preparations and reactions of ethers, let's talk about epoxides. All right, what is an epoxide first and foremost? That's an important question to answer. Well, an epoxide is a cyclic ether with a 3-atom ring. All right, so now for preparation of epoxides, one preparation method of an epoxide requires peroxy acids that have a molecular formula of RCO3H. Okay, so anything that looks like this, and the R group can be anything. All right, so whenever you see a structure that is similar to this, it has this carbonyl with OOH, R group can be anything. All right, this falls under the category of peroxy acid. And when it reacts with a double bond, what will happen is you're going to form an epoxide. This process is stereospecific, so substituents that are cis to each other in the starting alkene, all right, are going to remain cis to each other in the epoxide. So if we had two groups right here, when we form the epoxide, they stay the same, cis to each other. If they were trans, they would remain trans to each other in the epoxide you form. All right, so it's stereospecific in that sense. All right, so if you're starting with a cis alkene, when you treat it with a peroxy acid, yes, you're going to form a epoxide, but the R groups that are cis to each other remain cis to each other. If they were trans, when you treat it with peroxy acid to form your epoxide, then they are trans to each other. So make sure that you keep that in mind when you're drawing the final product for these kinds of reactions. Another preparation method is based from halohydrins. All right, alkenes can be converted into halohydrins when treated with a halogen in the presence of water. Halohydrins can then be converted into epoxides when you treat them with strong base. All right, this is kind of achieved through an intramolecular Williamson ether synthesis, right? So an alkoxide ion is formed, all right, through a proton transfer to begin with, all right, and then it functions as a nucleophile in an intramolecular and SN2 reaction, all right? So you have a double bond here. You can do your halohydrin reaction. This will add bromine and alcohol to your ring, all right? And then when you treat it with a strong acid, they'll attack each other and form an epoxide. Okay, so let's look at this mechanism in detail. First step, proton transfer. The hydroxide deprotonates the halohydrin. It deprotonates it, and it establishes an equilibrium with this alkoxide ion. Now we're going to get that intramolecular SN2, where the alkoxide ion functions as a nucleophile. This functions as a nucleophile, and it's going to attack right here to form that ring structure, and bromine is a leaving group. It leaves. All right, fantastic. So let's put this into play with some a few practice problems. All right, make sure that we have a good handle on these problems. Identify reactants that you would use to form the following epoxides. All right, so here's our epoxide. We're going to highlight it. Boom. All right, and then we're going to use a different color, something bright like orange. We're going to identify the groups attached to the epoxide, specifically here. All right, what are the 4 groups attached there? We have a methyl on a dash. We have this benzene ring on a wedge. We have another benzene ring on a dash and a hydrogen. Okay, so these 2 benzene rings, one is on a wedge and one is in a dash, they're trans to each other. All right, they're going to be trans to each other. So that's very important for us to keep in mind. All right, so we have our 4 groups, and we know that the 2 benzene rings have to be trans to each other. Our starting material has to have a double bond. All right, and now we just said the 2 rings have to be trans to each other. So they're going to have to go like this. All right, fantastic. Now, to this carbon, I'm going to highlight that carbon. Actually, let me get a red. All right, this carbon, which is drawn right here, has a benzene ring and a hydrogen. So we have to draw in that hydrogen. This other carbon right here, it has that benzene ring, which we've already drawn, and a methyl group. So we can't forget to put that. This is the starting double bond that we're going to work with. And what are we going to treat this with? Well, peroxy acid, obviously. So our CO3H. We're going to treat it with this. And what we get at the end is our final product, which is drawn here. I don't want to try to draw that again. That is a lot. All right. So very easy to figure out what your starting reactant is. All right. You look at your ring. That's your epoxide. Well, these 2 carbons right here is where we're going to start our double bond. So we're going to do B now. All right. What is attached to this bond right here? Well, we have on one side a hydrogen and a methyl, and on the other side a hydrogen and a ring. All right. Now, one hydrogen's on a wedge and one is on a dash, so we know they will be trans to each other. All right. And now on this side to the hydrogen, there's a methyl, so we have to draw that, and then a ring on the other side. So this is our starting double bond. And again, all we do is we treat it with some peroxy acid to get our final product, which is B. All right, fantastic. I will let you attempt C and let me know what you get. But lastly, for this chapter, we want to discuss reactions of epoxides, and we want to focus on ring opening reactions of epoxides. Epoxides, they form this like 3-ring structure, right? Well, believe it or not, they have significant ring strain. And so as a result of that strain, they're going to be reactive, uniquely reactive, all right? And they're going to undergo reactions that will allow the ring to open, okay? Which alleviates that strain. So when we're talking about ring opening reactions of epoxides, this is the basis of this conversation. Now, one way to do this ring opening of epoxide is using a strong nucleophile. When an epoxide is subjected to an attack by a strong nucleophile, say sodium hydroxide, a ring opening reaction will occur. All right, and what will happen is your ring will open. You're going to preserve these 2 carbons. All right. And of course, your alcohol here, your oxygen here will get protonated to form an alcohol group. And depending on what your nucleophile is, you can add some other group to the other side of when you open your ring. That depends on the nucleophile you use. Here we're using sodium hydroxide, so obviously we'll be adding a hydroxide when the ring opens. All right, you preserve the oxygen, it'll get protonated. All right, so you always have this alcohol group here. This other group depends on what your strong nucleophile is, and you can look at a table right here that will show you, depending on the nucleophile you use. If you use a sodium OR, then you're adding an OR group. If you're doing a nitrile, you add the nitrile group. SR, or if you do your Grignard reagents to open your ring, then you get to add whatever R group you want, methyl, phenyl, ethyl, whatever it is. And if you are using a reducing agent, then you get to add hydrogen on the other side of when your epoxide ring opens. All right, some things you need to consider when this is occurring are two things: regioselectivity and stereochemistry. All right, for regiochemistry, when the starting epoxide is unsymmetrical, all right, if there's some group here like a methyl, all right, when it's unsymmetrical epoxide, the nucleophile is going to attack the least substituted position. Okay, so keep that in mind. And then the second thing you want to keep in mind is stereochemistry. All right, when the attack takes place at a chiral center, what you're going to see is inversion of configuration. All right, and that pretty much summarizes ring opening reactions of epoxides with strong nucleophiles. Ring opening reactions can also happen with under acidic conditions, so acid catalyzed. As an example, right, consider this epoxide being treated by a very strong acid. You get the ring opening, all right, where you preserve this alcohol group. Your oxygen opens and it gets protonated, obviously, so you have an alcohol group. And your second group is the whatever halogen you have in your alkyl halide that you're treating the epoxide with. All right, so things to consider here is mostly regioselective. When the starting epoxide is unsymmetrical, all right, the outcome depends on the nature of the epoxide. So if you have an epoxide, one side is primary and the other side is secondary, the attack is going to take place at the least hindered primary position. All right, just as we would expect for an SN2 process, and this makes sense considering steric effects. Now, when one side of the epoxide is primary and the other is tertiary, okay, you might be quick to say primary, but here you have to consider electronic effects. All right, electronic effects here are going to prevail over steric effects. What will actually happen is the reaction is going to be observed to occur at the tertiary site, the more substituted site. All right, so this is a lot to talk about for ring opening reactions of epoxides. Let's just go ahead and jump into a practice problem. All right, our last final problems of OChem 1, bittersweet. And this problem asks us to, for each reaction, predict the product and draw the mechanism for the formation. Fantastic. So we have an epoxide and we're treating it with a strong acid. All right, so this is going to be our acid catalyzed hydration. And I thought I would do this problem so I can show you the mechanism for acid catalyzed as we do this problem. All right, we're treating it with HCl. What happens first, all right, and it's kind of about equilibrium arrow. All right, here's your HCl. Your alcohol, your oxygen is going to take that hydrogen. All right, and then we're going to break off from the chlorine. So what we get now is we still have our ring structure, but now our alcohol has a hydrogen and a positive charge. Now, what the chlorine does is it comes in and it attacks a carbon. Now, they're both symmetrical, so it doesn't matter which carbon. And then we break this bond like so. All right, and what we get as an end product is we have our alcohol here and we have our chlorine here. Fantastic. Now, let's do B. All right, here is our group and here's our methyl. We have a methyl right here. We're treating it with HBr. All right, so again, what happens is our HBr, our oxygen is going to steal that hydrogen. It's going to form something that looks like this with a positive charge. Then our bromine comes in. All right, and there's a methyl right here. Our bromine comes in. Where's our bromine going to attack? Well, we have a primary position and a secondary position. It's going to take the primary position, right? Because when it's primary versus secondary, primary wins. All right. Now, if it was primary versus tertiary, then tertiary would win. All right. So keep that trend in mind. Here we have primary and secondary, so it's obviously going to take the primary position because of steric effect reasons. So our bromine will come and attack right here. This will break up, and what we get as a product is something that looks like this. I don't draw these lines as appropriately as I should for a bond, forgive me. All right, and boom, there we go. Fantastic. All right, now it doesn't seem like I have an example problem where it's ring opening through strong nucleophile. So I'm going to come up with my own example problem, and we're going to do it so we can also practice ring opening reactions for epoxides with strong nucleophiles. So let's pretend we have a ring that looks like this. All right, and we have a phenyl here and let's say ethyl here, whatever. Okay, and we're going to treat it with sodium ethoxide. All right, we're going to treat it with sodium ethoxide and, of course, water. All right, what is going to happen here? I'm going to draw the mechanism for this while we do it as well. Well, you have your ethoxide here. And the first step for strong nucleophile is not to protonate the oxygen, but actually to have your nucleophile attack a position that's less sterically hindered. Okay, fantastic. And what we're going to get is it's going to have a ring opening. We've got our oxygen with our negative charge now. All right, our ethoxide has added itself here. And of course, we still preserve our phenyl group that's right here at this carbon, close. All right, and our methyl group right here. And if you get confused with which carbon is which, you can always just highlight them. All right, to keep track of it. Our ethoxide added at that carbon, and these are where our two substituents are. Fantastic. Now what can happen is our water can come in, HOH, and now our oxygen is going to steal a hydrogen from our water. All right, and what we get is now we've have this alcohol group, we have our ethoxide group, and of course we have preserved our two substituents. Nothing happens to them, and this is our final product. So what you notice is for ring opening reactions of epoxides, your first step is going to be nucleophilic attack, then proton transfer. For acid catalyzed, it was the other way around. Proton transfer, then attack. All right, fantastic. That is all I have for you today. If you have any questions, let me know. If you need any help studying for finals, reach out for advice, anything like that. I like to make myself available for you. Other than that, you did it. You made it to the end, and I'm proud. Good luck, happy studying, and have a beautiful day.